Sound is usually something we only experience through our ears, but it is also a physical force, a vibration that travels through the air, pushes against the physical environment, and is capable of organizing the matter around us into complex geometry. In this video, we're going to build a DIY Cymatics rig. Step by step, we will take an everyday speaker and some basic household items and turn them into a scientific instrument that makes sound visible. By bridging the gap between the auditory and visual worlds, we can map out exactly what our favorite music, or even our own voices, physically look like. Before we start building the rig, we need to understand the physics of resonance. Every physical object, whether it's a wine glass, a guitar string, or a metal plate, has a specific natural frequency that it naturally likes to vibrate at. When you feed an object its exact resonant frequency, the energy travels through the material, hits the edges, and bounces back. If the timing is precise, those returning waves reinforce the new ones, creating what physicists call a standing wave. Inside this standing wave, there are distinct zones. The antinodes are the areas experiencing maximum, violent movement. But between them are the nodes, points where the opposing waves cancel each other out, leaving the surface completely still. This interaction between nodes and antinodes drives all cymatic art. When you place a material like sand or water on a vibrating surface, it will be violently pushed away from the chaotic antinodes until it finds a safe place to settle in the peaceful, motionless nodes. Let's assemble the hardware. You will need a spare speaker, a mini amplifier, a smartphone or tablet running a tone generator app, a lightweight spacer like half of a plastic Easter egg, and a rigid flat plate. The most critical step in construction is attaching your spacer. You need to glue the plastic egg half directly to the center of the speaker's moving cone. Make absolutely sure you do not get any glue on the stationary outer housing, or the cone won't be able to move freely. Next, take your flat metal or plastic plate and secure it to the top of the spacer. This connection needs to be rigid so that the vibrations transfer efficiently from the speaker, up through the spacer, and into the plate. With that mechanical linkage complete, any digital audio signal you play from your phone is now translated into physical movement, effectively creating a highly controllable, localized earthquake across the surface of your plate. Now for the first test. Sprinkle a very light, even layer of sand or salt across the top of the plate. Keep it sparse. Too much material will weigh the plate down and result in a muddy, unresponsive mess. This method dates back to the late 1700s. German physicist Ernst Chladni originally mapped these exact acoustic phenomena by dragging a violin bow along the edge of a sand-strewn brass plate. Open the tone generator app on your device. Start at a low pitch and slowly sweep the frequency upward. At first, the sand will just bounce around chaotically. Keep sweeping until you hit a resonant frequency. The moment you do, that disorganized sand will instantly snap into a sharp, perfectly symmetrical geometric shape. The pitch directly dictates the visual complexity. As you push the frequency higher and higher, the wavelengths get shorter, generating increasingly intricate, multi-layered nodal patterns on the plate. This experiment proves that every musical note produces a specific, repeatable visual fingerprint, completely dictated by the physical boundaries of the plate it vibrates within. Now let's move from solid to liquid. Remove the flat plate and replace it with a shallow dish of water. This allows us to capture fluid, three-dimensional vibrations. Liquid cymatics introduces a major challenge: lighting. Without the right light setup, the rapid water ripples will just look like a blurry, invisible mess to your camera. To fix this, you must place a ring light directly above the water. Ensure it is perfectly on axis with your camera lens so it catches the surface reflections directly. With the lighting set, play a pure tone into the speaker. The reflection will reveal a sharp, shimmering geometric topography dancing across the surface of the water. We can expand this experiment by playing the sound of complex acoustic instruments through the rig. For example, testing the deep, rich overtones of a traditional bronze gong produces an entirely different set of complex wave interactions. You can even test a recording of a human voice. Because vocal waveforms are incredibly complex and constantly shifting, they generate rapidly morphing, highly organic visual patterns in the water. Replacing pure digital tones with live vocals and instruments transforms the rig into a dynamic, real-time canvas that captures the raw character of sound. We started with a disassembled everyday speaker. Now we have a customized scientific instrument capable of mapping the physical geometry of sound waves. Now it's your turn to push the experiment further. Change the shape of the plate, test thicker viscous liquids, or play your favorite song through the amplifier to discover its unique visual signature. Sound is a fundamental architectural force that actively organizes and shapes the matter around us.